Hi, my name is Jeb Trey, and I've been working in the Computer Systems Lab on my research project for this year. So I want to start off today with a simple question. Have you ever seen a yo-yo this big before? Well, this oversized yo-yo is called a Diabolo or a Chinese yo-yo, and it can do everything a yo-yo can and more. I can do so many cool tricks using two sticks controlling the Diabolo. And sometimes the Diabolo moves at speeds as which the normal human eye can't really tell what's going on. So that's where motion capture comes in. Motion capture allows us to record information about this Diabolo that we might otherwise not be able to tell. As stated in my project title, I used the motion capture system at TJ to analyze Diabolo juggling and different movements to improve on state-of-the-art models. So let's see what I have in store for today. I'm going to start off with talking about some background about the Diabolo and CS research done on it. Then I'm going to go into the specifics on the methods I've used for this project, including how I use Vicon, models, and Flask. And then I'm going to go through my results, like comparing the models and describing them versus the previous models. And I'm going to talk a little bit about how my research can be taken further in the future. So a little background on Diabolo research. Dragulski et al. Made a Diabolo predictor that predicts the next state of the Diabolo based on the current state and the stick positions. It uses a forward Euler method, so you might have heard of the Euler method in AP Calculus. It's the same Euler method I mentioned here. And it uses some constraints to limit how the Euler method predicts the values. Then Morica et al. Uses their algorithm called Diabolo Manipulation Net to predict the Diabolo position and is trained on Diabolo's pitch, yaw, and also the robot's arm height differences between the robots and also the speed of the robots. So both of these models help these researchers create code that allow these robots to play around with the Diabolo and do cool tricks with them. I'm going to talk about my methods more in depth in this section. I used the Vicon motion capture system for my project. So the Vicon motion tracker software can actually process all the information from the motion capture system and produce a large data set that I can use for my analysis. Here, the TV is showing what I see when I bring up the tracker software. The software connects with the 9 cameras located in the web lab and can see the setup right here on the right. I did my Diabolo performances in the middle of this setup. Within the setup, there are several MX-T20s and T40s cameras, and right there in the middle is an image of an MXT camera. And the white ring you can see is actually what beams out the infrared light that helps track the motions of the objects. And inside that ring, there is a camera that has sensors to detect what is reflected back. In order for the cameras to detect the objects, I have to put markers on the objects. Basically, they're retroreflective markers that specifically are made for motion capture. And for each of my Diabolo performance, I take around a minute or two to record it. And that allows me to get all the data I need for specific movements like changes in pitch or acceleration. Here's a side-by-side demonstration of me using the motion capture system. On the left is what I was physically doing in the classroom, and I'm showing a bouncing trick here. On the right is what the Vicon tracker software displays. It shows the movement information about the markers and objects. Let's talk about the Diabolo models. The first part is the analytical model that I built on top of Dragulski et al.'s model. By incorporating orientation prediction, specifically predicting pitch, I then tested their models and also my pitch predicting addition to analyze the prediction abilities of these algorithms. The pitch is predicted based on stick offset position and also how fast the Diabolo is spinning, the angular velocity. The reason why I use the stick offset position is that an article by Residual et al. Called Diabolo Skill Analysis showed evidence of the relationship. Using mechanics insights from physics, I also determined that angular velocity also had an effect. During the implementation, I manually transpiled the researcher's algorithm from C++ into Python. This is for several reasons. My site is built on Python, so I converted it to integrate better into my website. In addition, all the machine learning libraries I know how to use are also in Python. Moreover, this also removes the C++ specific library dependencies and allows it to be more flexible and less dependent on those specific libraries. Many of these libraries are not found in Python or other languages. So here you can actually see a diagram Dragosky et al. Used in their article. And this shows how their prediction algorithm was based on Diabolo position and also different factors like velocity, which predicted the next Diabolo position. Here's a pseudocode version of my pitch prediction algorithm. It might seem a little complex, but basically the first for loop calculates all the offset plus the first pitch value. And then the second for loop does an Euler method prediction for the pitch values based on the approximation for the derivative as shown here. And the line in between the for loops is just a Stavisky-Golay filter which smooths out my data because there's some noise. And it helps the predictor have better predicting ability as well. The diagram on the side is a profile view of the Diabolo, and the axis is basically what I base the pitch on depending on how the Diabolo tips up or down. The second part of my project is the residual physics learning neural network. Don't confuse this with residual neural networks as in ResNet. This is something different. And this really focuses on the principle that analytical models deviates from real-life values. No model is ever perfect, so there's always going to be some error. But with residual physics learning neural network, you can predict the difference and try to reconcile the model values with the real-life values. Dragosky et al. Showed that neural networks by themselves don't work well. But Zen et al. In TossingBot showed that residual physics learning can be better. For residual learning neural network, I used the TensorFlow library and the Corrales library for creating the model. For the input to this sequential model, I used the current Diabolo stick placement, and for the output, I used the correction for the next time step. And it's basically the difference between the real-life value and what my analytical model predicts. The layer of the sequential model consists of 3 hidden layers of 100 nodes each using ReLU activation functions. This is a standard structure for neural networks. And for training, I did around 300 epochs with batch size of 100. I built my site on a Python web framework called Flask. In addition, the backend included some other aspects like my actual model consisting of the analytical and machine learning model that runs the predictions. I also used Gazebo for 3D graphics and simulation. I used it for the 3D models of the Diabolo and sticks for my site. I also added the feature of Vicon data streaming in order to stream data directly onto my site from the Vicon tracker software. And this is just really for convenience and for anyone else who might use this site. In addition, the front end is mainly built with JavaScript, and it's connected with Gazebo and displays the object movements. This allows the motion capture data I recorded and also model predictions to be visualized easily on my site. One of the simplest but most useful feature I mentioned is probably the Vicon data streaming button. As shown here, I'm connected to the Vicon system, and I'm toggling on the data stream. It starts streaming values about the objects present, so the Diabolo, stick left, and stick right. Then, once I'm done streaming, I can press the toggle button again, which stops the stream and downloads a file of all the data that was sent to my site. In order to display Diabolo movements, I need to connect to a Gazebo server, and I got one running at this IP address. Once I'm connected, I can upload a recording like this. And then pressing the play button allows me to display what moves I recorded. Additionally, I can also upload a dataset that I want to do a prediction on by using the same upload button. Then I can press the run simulation button and wait for it to finish. The download button allows me to download the data back from the website. I have several website functionalities as described on the previous slide, and in addition, specifically about the ability of my predictors, the residual physics learning network's prediction had a mean squared error of 0.132 meters squared. For context, the Diabolo's possible XYZ and pitch values have a range of around 1.685 meters. Then, when comparing the residual learning network with our analytical model, adding the residual physics learning neural network model resulted in a mean squared error of 0.188, which is significantly lower than the mean squared error of the analytical model by itself, which had a value of 0.771. This shows a significant improvement using the residual physics learning neural network and shows that this has positive results. There are many possibilities and future research directions for my project. For example, in order for this to be really practical, the analytical model should be more efficient since it runs on the magnitude of minutes currently. Additionally, I talked about pitch prediction, but yaw prediction can be added, and this diagram here is a top-down view of a Diabolo, and it shows how yaw is the Diabolo turning left or right. Also, I can use more ML model designs like different hidden layer sizes, different hidden layer counts, or a 1v1 strategy to add some variation to the ML model, which could bring improvements to my project. Moreover, for my project, I use a triple bearing axle Diabolo, but there's also fixed axle Diabolos available, and here are a picture comparing the two axles. The blue Diabolo is a triple bearing axle, and the red Diabolo is a fixed axle. Using fixed axles can be further research for this project. If you're interested in checking out my website, you can visit my site at the link on your screen right now. It's bit.ly/jebtray-syslab.